Okay, so hopefully this video won't be particularly long. I'm going to go ahead and go over two pieces. One is to how to simplify a trigonometric expression, and the other one is to actually solve an equation that's trig-based. So let's head right on in here. I have a series of questions ready to go. These problems right here, I've often had students find them to be somewhat challenging when you're trying to simplify some kind of a trig expression using identities. So the first thing that I personally like to do if I'm solving a trig identity, if it doesn't have that, I like to turn it into sines and cosines. So earlier on, we mentioned that a secant is a 1 over the cosine. So I'm going to leave the sine that I previously had where it was, but then I'm going to go ahead and do one extra little piece, and the secant that was here, I'm going to express that as a cosine because that was one of our fundamental identities, that a cosine is a reciprocal of a secant. Now, I'm going to go ahead and leave this other one alone, and let's just look back to our days, back in elementary school, if you will. Much harder than elementary school, granted, but if we're going to take two fractions and subtract them, then we definitely need to have a common denominator. So what I'm going to do is I'm going to go ahead and multiply this fraction over here by a sign on top and a sign on the bottom, because as such, each of these fractions will have the same denominator, sine, cosine. Okay. So when you add or subtract fractions, you get that common denominator, and that's just what you have. And then you either add the numerators or subtract the numerators. So we have my 1, and I'm supposed to subtract a sine times a sine, which is a sine squared. Well, every single time you see that sine squared, you should be like, alert, alert, something big has happened, because our Pythagorean identity from one of the previous videos or from class is that sine squared plus cosine squared is 1. And we can very quickly see that if you rewrote this just a little bit, that 1 take away the sine squared would be cosine squared. So my first thing was to turn this two things into one thing. And then notice that if you have a cosine squared and a cosine on the bottom, those would cancel, and I'm left with cosine over sine. And honestly, I would be good if you left it there, but if you looked at the back of the book, most people would accept a different answer a little bit better, that a cosine over a sine is actually a cotangent. So that's a pretty simple idea, because again, if our idea is to simplify, you don't get much easier than just saying cotangent. Pretty simple little idea. Okay. Number 2, kind of a distinctive problem. Something weird happens in this thing. And this is just one of those tricks that math teachers do that drive people crazy, because they just, why would you do that? Well, I do it because I've seen it before. But whenever I see a 1 minus and a 1 plus or something like that, what I like to do is I like to multiply each one by the other. And it turns out that is really an equivalent thing to do with what we did in the first problem, because if I have two fractions, which I do, and I need a common denominator, this one has a 1 minus cosine, so I'll give this one a 1 plus. In the same way, this one has a 1 plus, so I'll give it a 1 minus. I'm really doing the same thing I did up here, creating that common denominator. Now, as such, I'm going to take it one little step at a time. 1 plus cosine times 1 is pretty simple. 1 minus cosine times 1 is 1 minus cosine. Here comes the important part. As it turns out, when you have these stories, 1 plus times 1 minus cosine right here, if you distributed it out, you'd get 1 times 1 is 1. You get a negative cosine and a positive cosine, which cancel out. But then right here, you get a negative cosine squared. And both of these things have the same idea. Now, in putting that together, as soon as we have a common denominator, we can then put those numerators together. And you're going to notice quite quickly that when you add these numerators, 1 plus 1 is 2, but a positive cosine plus a negative cosine is going to be 0. So we're kind of set, but that same thing is going to happen again. You're going to see this over and over and over again, that right here, 1 minus the cosine squared, hopefully you can see that 1 minus the cosine squared, look right up here, 1 minus cosine squared is the sine squared, which again, that's an answer that I personally really, really like, but we could also write that equivalently as 2 cosecant squareds. And that's usually considered a little bit better answer. Now, my last one is kind of like the irony question. And that's because if you look at what happened here, you see how the 1 plus cosine times 1 minus cosine became 1 minus cosine squared? Sometimes it's beneficial to kind of go the other way. And what I see is if 1 plus cosine times 1 minus cosine is 1 minus cosine squared, then I could kind of go the other way and say that 1 minus sine squared is 1 plus sine times 1 minus sine. So instead of actually multiplying the top out, I kind of went backwards and kind of undid it. I factored. Now, if we rewrite that way, you're going to notice that those would cancel, and all of a sudden we're down very quickly to just simply 1 minus sine, and we're done. That's it. There's nothing more that I could do to that problem to make it easier. That's simplifying. Now, one of the downsides of simplifying is how do you know when you're done? How many steps do you do? Wish I could tell you. Sometimes you just have to play with it and hope that you did enough. And if you get it down to a single thing like this, like these are pretty clear, but sometimes you do some work and you don't know, did I do enough? And all you can do is just over time with some experience, you'll learn what actually works and what doesn't. Now, here's the other piece of the puzzle. We are now going from what are called expressions, where it was just, hey, simplify it, make it look better. This is saying solve. In other words, I want to know what value of x actually makes this thing true. That if I took the cosine, I took the sine, I evaluated it, multiplied it by 2, subtract the cosine, somehow I get 0. Like, what angle does that? Well, there's actually an infinite number of answers that do that. So usually we just take all the answers from 0 to 2 pi to satisfy this. We are going to do some unit circle here in just a moment. But the first little trick that you've learned back from Algebra 1 is to look for common factors. And I noticed that these things both have a cosine in common. So I'm going to factor out a cosine. And if I did, take the cosine of this first term, I'm left with 2 and a sine. Take the cosine out of this one, and I'm left with a -1. And now I have a product. And the idea is going back to Algebra 2, and in fact, a little bit before that, we've used the zero product property. And the only way that this product can be 0 is if either the cosine itself is 0, or if the sine itself is actually 1/2, because 2 sine minus 1 would be 0. You could move the 1 across and divide by 2. Well, hey, we're back to the unit circle. So if we think through the values of the unit circle that make it make sense, I mean, I hate doing this over and over and over again, but we know some of these values. I guess I'll put them in here because we're going to need it for the next little bit. It's pi over 3 and pi over 2. So the question right off the bat, sine, cosine, and tangent. I'm only going to need these first couple. Boy, I wrote that way too small. It's hard to see that. So when is the cosine 0? Well, that happens at, oops, when is the cosine 0? Well, that happened over here at pi over 2. But as it turns out, pi over 2 is not the only answer. 3 pi over 2 works itself because, remember, the x value is 0 here. That's 0, 1, and 0, -1 at 0 and 3 pi over 2. And the sine would be 1/2 at pi over 6, but based on ASTC, there's a secondary piece right here at 5 pi over 6. So those are the two values, or actually the 4 values that would make sense. Now, when I do those kind of problems, sometimes I don't feel super duper comfy with them. And so I'll double check by doing just a quick look at Desmos or on my graphing calculator to see if I'm right. So let's see what happens if we go back and we take a look at the original question. And I'm going to pause this for just a second. Big. Math department. Send me the message and I'll do it. Okay. Yeah, tell us how to do that. Okay. Bye. Okay, so I'm back. Sorry about that. So I'm going to type in 2 cosine x, sine x, and minus the cosine of x. And I guess I need to put maybe like a y equal in there. And maybe I need, I thought that would do it for me. I guess maybe I need some parentheses in there. Oh, there we are. That's a funny little thing. So notice that I got this crazy looking function right here that has 1, 2, 3, 4 places between 0 and 2 pi. And you're going to notice those line up absolutely perfectly with what we have. Notice that strange looking wave. That's what happens when you start multiplying and adding different sine waves. And that's actually foreshadowing, because honestly, when you look at light and you look at sound, you're just taking different waves that are blending together. You know how yellow and blue make green. Well, a yellow light wave is different than a blue light wave, but if you add them together, you get some other kind of complex wave that puts those two things together. So anyway, let's go back to here and let's look at the next one. In the next problem, I want to know when is the sine times the tangent squared the same as the sine. Well, one of the things that I have tried to emphasize with you guys this year is avoid the idea of dividing both sides by something. Don't do that, because if the sine ever hit 0, you'd be dividing by 0. And we know that the sine hits 0. The sine hits 0 at 0 and at pi. So instead of dividing by the sine, let's move that across and then follow the lead of what we did in this first problem. And what I would have is, since these terms both have a sine in it, I would factor a sine out, and I'm left with a tangent squared in this piece and a -1 in that piece. Well, we're getting there, because I'm going to take a little play out of the playbook from Algebra 2 and before. This is a difference of squares. So this would be a tangent +1 times a tangent -1. And that leads me to the fact that if this is true, then either the sine is 0, which I've already mentioned happened at 0 and pi, or the tangent is -1. And I know the tangent is -1, again, going back through this story in these two quadrants at 3 pi over 4 and 7 pi over 4. Or last but not least, the tangent could be 1, which happens at 1 pi over 4, and I think 5 pi over 4 down in the first and the fourth quadrant. So it looks to me like I've got 1, 2, 3, 4, 5, 6 answers this time. That's a lot. This would be a tough problem for people. So let's go ahead and take a look and see if we actually captured all that data, because that just seems like a lot to me. So let's see what happens. So let's go back here, and I've got the sine of x. I've got the tangent of x squared. And I want to know, when is that? Okay, why does it not like that? I guess I'll put a times there in the middle. Sine of x times the tangent of x squared. I don't know why it doesn't like this thing. Sine of x. Maybe it needs a parentheses around that. Oh my goodness, it did. It wanted a parentheses there. And I wanted to know, when is that equal to just the sine of x? Well, if you see those two waves kind of crisscrossing together, it looks like they hit here at 0. They hit here at pi over 4, 3 pi over 4, pi, 5 pi over 4, 7 pi over 4, and back to 2 pi. But you'll notice that in my list, I didn't include 2 pi because it was just a repeat of pi of 0 itself. Okay, my last one. Here we go. Let's get onto our last little guy, and then we're off to the races. Now, this is a little bit of a different story. This looks pretty simplistic. So remember over here, I said, let's not divide both sides by the sine, because we might divide by 0. But that doesn't mean I can't divide by 2. 2 is a pretty nice number. There's no way I'm dividing by 0, because I'm literally dividing by 2. So when I go to take the square root of both sides, that's plus or minus the square root of 1/2, which is actually root 2 over 2, which we've seen a few times. And I know that the sine is root 2 over 2 at pi over 4. But again, I don't just want the positive ones, I also want the negative ones. So I want the one in the first quadrant where it's positive. I want the second quadrant where it's also positive, the third quadrant where it's negative, and the fourth quadrant where it's also negative. So it appears to me that if I did that problem right, I should have 4 answers for that one. And let's go ahead and do one last take a look at Desmos and see if we picked the right set of answers. So what I had on this was 2. Let's make that a 2, and let's make this a sine of x squared. Okay, let's go ahead. Oh, I guess I don't want that. So there's 2 sine of x squared, and I this time wanted that number to be equal to the number 1. So let's see, it looks like it hit here at 1 pi over 4, here at 3 pi over 4. Let's scroll that down, 1 pi over 4. It looks like 3, 5, and 7. Looks like we did okay. And there's all sorts of ways that you could do that. Some people would have divided both sides by 2 and said, well, then I took this thing and I now set it equal to a half. But you're still going to get the same answers. We're just going to have it in a slightly different viewing window. So anyway, that's a little idea of how do you solve equations and also how do you simplify expressions using those fundamental identities. And that's the end of 5.1 as far as I can tell. All right, I'll see you back in class.